Hi everyone, welcome to my channel Physics Classes. Today I am going to talk about Lenz law, which is a fundamental phenomenon of electromagnetic induction. So before getting started, please don't forget to subscribe my channel and press the bell icon so that you get a notification whenever I upload a video in my channel. Now let's have a look on Faraday's laws. Faraday's laws of electromagnetic induction tell us that an electromotive force or EMF will induce in a coil if you try to change the magnetic flux which is passing through the coil. This means a current will induce in the coil once you try to change the number of magnetic field lines that passes through the coil. For example, suppose you try to move this bar magnet towards this conductor loop which is connected to a galvanometer. Now, as you move the magnet, you will find that the magnetic field lines that passes through the coil are also changing. So an EMF will induce in this coil and current flows along the coil and you will see a deflection on the galvanometer. Similar phenomenon happen again when you move the magnet away from the coil. But this time the galvanometer shows a deflection which is opposite to the previous case. So Faraday came to the conclusion that the induced EMF is proportional to the rate of change of magnetic flux that passes through the coil. Guys, I have made a detailed video on Faraday's laws on YouTube, and if you want to know more about Faraday's laws, the link is given in the description section. So guys, here J is the EMF induced on this coil and d phi dt is the rate of change of flux passing through this coil. And here n is the number of turns of this coil. Suppose if there are two numbers of turns, so you have to put 2 here. And this negative sign says that the direction of this induced EMF opposes the rate of change of magnetic flux. Now let's understand how magnetic field generates due to current carrying conductor. Now, if a steady current I flows through a conductor, a magnetic field generates around the conductor and its field strength decreases as you go far from the conductor. The direction of this magnetic field can be found out by right-hand rule, which says that if you grasp the wire with your right hand so that your thumbs point in the direction of the current, then your fingers will encircle the wire in the direction of the magnetic field. So when current flows through a coil having multiple turns, which is known as solenoid, it produces a magnetic field which leaves from one end and enters to the other one. For a long solenoid with closely packed coils, the field is nearly uniform and parallel to the solenoid axis within the entire cross-section. The field outside the solenoid is very weak compared to the field inside, except near the ends. Therefore, a solenoid more looks like a bar magnet with opposite polarities on each ends. Again, instead of a solenoid, if current flows through a coil with a single turn, the magnetic field lines look like this. It seems that magnetic field lines emerges from one surface of the coil and terminates on the other side. So again, we can say that a current carrying loop behaves as a tiny magnet. So we have learned that a solenoid or a current carrying coil acts like a bar magnet. Now let's find out the polarity of such solenoid if current is flowing in a particular direction. Suppose in this figure current is flowing in this way and you are looking the solenoid from its right. So you will find that the current is flowing in a counterclockwise direction. If the current flows in a counterclockwise direction, then that side of the solenoid will act like a north pole. On the other hand, if you look the solenoid from its left, you will see that the current is flowing in clockwise direction. Now if the current flows in clockwise direction, then that end of the solenoid acts as a south pole. Now you can remember the current direction and the polarity of the solenoid by a simple method. You just need to add arrows on N and S in this direction. So for north pole, current is in counterclockwise direction, whereas for south pole, it is clockwise direction. Now we are in a good position to discuss about Lenz law. According to Lenz law, if you try to change the magnetic flux passing through a coil, an induced current will generate in such a direction that it will oppose the original change of magnetic flux. Now suppose you are moving the north pole of a magnet towards a coil which is connected to a galvanometer. As you move the magnet, the number of magnetic field lines passing through this coil, that is, the magnetic flux, is also changing. In this case, the magnetic flux increases. So, in order to oppose this change of flux, a current will induce in the coil in such a direction that the magnetic field produced by this current opposes the original change of flux. Therefore, in this case, the direction of the current will be counterclockwise such that a north pole will form on the surface of the coil, which is facing on the north pole of the bar magnet. Similarly, if you move the north pole of the magnet away from the coil, the magnetic flux increases. And so the direction of the induced current will be clockwise to produce a south pole on the surface which is facing the north pole. Now let's have a look on different cases when Lenz law is applied. For example, in figure A, the magnetic field lines are towards the plane of the paper. Suppose the coil 1 strings to coil 2. So the surface area of the coil decreases and therefore the number of magnetic field lines passing through the surface also decreases. Therefore, in this case, the induced current will be in clockwise direction so that it produces its own magnetic field to make up the reduction of magnetic flux. On the other hand, in figure B, let the magnetic field is along the negative x direction. Initially, consider a coil whose surface is in the xy plane. Now suppose you start rotating the coil along the y-axis as shown in the figure. As you rotate the coil, you will find that the magnetic flux through the coil increases. So to counter this change, the induced current will be in counterclockwise direction. Now look at the figure C. Suppose you try to push the rectangular coil in a region where magnetic field exists. Now as you push the coil, the magnetic flux through the coil increases, and to counter this, induced current will be in counterclockwise direction. Similarly, look at the figure D. The magnetic field is along the x direction and the surface of the coil is in xy plane. Now suppose you start moving the magnet along the x-axis. In this case, no current will induce in the coil since no magnetic flux through the coil has been changed. Now let us consider what would happen if Lenz law were not true. That is, when you move the north pole of the magnet towards the coil, an induced current generates a south pole on the surface of the coil which is facing the bar magnet. The induced current in this imaginary situation would produce a flux in the same direction as the original change. So, the greater change in the flux would produce even larger current followed by still greater changes in flux and so on. The current would continue to grow indefinitely, producing power even after the original stimulus ended. This would violate the law of conservation energy. So Lenz's law is always true, so that laws of conservation of energy sustain.